Okay then, so let's continue with the next part here. VTC is data dependent. So what it's trying to say here is that we're trying to see what is the speed or the propagation delay of your logic gate. We've seen the TPHL, TPLH of the inverter, and the inverter is only one set of input is possible. Okay, meaning you can only put a 0 or a 1. For a logic gate, for example, here this is a NAND gate. So for the NAND gate, you can put AB as there's 4 possible combinations of inputs. You can have a 0, 0, 0, 1, 1, 0, and 1, 1. And each combination of input actually will give basically a different speed and different VTC. So we can see here, for example, on the graph. So if you give AB both 1, okay, AB transition from 0 to 1. So if you give a 1, it will start to pull down, and in this case both the PMOS are either on or off together. When on, WP effectively is doubled with respect to the inverter circuit, hence VTC moves to the right. So you can see that the VTC actually depends on the set of input that you give. Okay, we'll see more example later on. Another issue here is with the threshold voltage. Okay, so the threshold voltage of M2 is higher than M1 due to the body effect gamma. So we can see here that the M2 is actually higher VT, VSB is not equals to 0. Okay, so here is normal. So for M1 is okay. You have the VT 0, but for M2 the threshold voltage is a little bit higher, and therefore what is the impact when the threshold voltage is higher? Then this M2 will be slower. So you can say impact M2 is slower. Okay, so if M2 switch on slower, then you're gonna have a higher delay. Okay, a higher delay, especially on the high to low transition. Okay, so these are the issues that we need to think about. That one is the delay is actually dependent on the input that you give, and number 2, the threshold voltage are not constant anymore for all transistors. Okay, so the switch delay model, we've seen this already in the inverter. So basically you can replace a transistor with a series connection between a resistor and a switch. Okay, so the same thing. So if you replace this, you can analyze in terms of logic level. Okay, logic 0, logic 1, instead of looking maybe at the voltage level. Okay, so let's have a look on the input patterns effect on the delay. So delay is dependent on the pattern of the inputs. Low to high output transition. So low to high output transition. So in the case of the both inputs go low. Okay, so 0, 0 on A and B. So if you put 0, 0 on A and B, which one is on? So your PMOS is on, so it's going to charge quite fast, right? Because now you have the resistors in parallel. Okay, so your delay is actually 0.69 RP over 2 CL. However, if only one input goes low and the other one is high, we are still going to charge the CL, but in this case your delay is a little bit higher, 0.69 RPCL. Okay, because now you only charge through one transistor instead of 2. So remember, if you charge to 2 transistors, it will be a lot faster than charging through one transistor. Now what about the discharging? So high to low output transition, discharging. So when both inputs go high, when you go 1, 1, this one off, and it's going to discharge, and the discharge depends on, now you have a series Rn resistance, so your delay is 0.69 to RNCL. Okay, so you can see that this one are all different delay values or different delay parameters. Okay, so here is some experiment that they did. So you can see that if you supply the input data pattern A and B both transition from 0 to 1, we get the 80 picosecond delay. Okay, this kind of inputs 70, 70, 80, 150, 130. So the fastest is so here A1, B0 to 1, so discharging. So the fastest is discharging through the NMOS, where only one of the input is transition from 0 to 1. And the slowest is actually charging. Okay, so this one is A maintain 1, B going from 1 to 0, so it's trying to charge your output CL and results in the slowest delay. So you have a different delay, so you have to be careful what is your input value and how it's going to impact. Okay, so let's look at transistor sizing. So transistor sizing is very important, as we've seen in the previous chapter on the inverter. Transistor sizing will impact the VTC, the VM, and also the propagation delay, the high to low and low to high propagation delays. So we've seen already how to size the transistors, and if you remember for the we've seen already how to size the inverters, and if you remember for the inverter, the resistance of the PMOS is roughly twice of the NMOS. So let's look at the inverter, review back our inverter sizing. So if you remember, we put a ratio of 2 to 1. So the size of the PMOS is, we make roughly 2 times wider W. So remember the L is constant, is the same. So we make the W of the P 2 times wider compared to the W of the NMOS because of the resistance. So basically, when we size logic gates, complex gates, we want the effective capacitance, okay, the effective size of the PMOS side 2 times bigger than the effective size of the NMOS side. Okay, so here let's look at the example for the so this is your NAND gate, and this is your NOR gate. Okay, so here actually when we talk about the size, we want the objective is to have a worst case TPHL, TPLH the same. Okay, the worst case delay the same. So for TPLH, okay, so the worst case is charging through one transistor, okay, and here the size is size 2. Okay, so you can say that the the CP, okay, the capacitance, let's say 2 picofarad on this side, okay, and on CN, okay, so we have the capacitance in the capacitance in series. So if you imagine the capacitance in series, okay, so here CN size 2, so CN is equals to 2 times 2 over 2 plus 2 is equals to 1, okay, and therefore your CP over CN is equals to 2 over 1. Okay, so here we can see that this is for your TPHL, okay, discharging. So this discharging effective size for discharging is 1, and the effective size for charging worst case is just 2. Okay, so then your ratio of the PMOS and NMOS is 2 to 1, and we should get roughly the same TPLH, TPHL with VM roughly in the middle. Now let's look at the NOR example. So in the NOR is the same case here. So to discharge the whole thing, the effective size CP is going to be 4 times 4 over 4 plus 4. That will be 16 over 8 equals to 2. And then here, remember, we just take the worst case. So the worst case is discharging only through this one off. Okay, here is off, here is on, and the effective size CN is only equals to 1. Okay, going to the worst case transistor, so your CP over CN is equals to 2 over 1. equals to 2. So then you should have roughly the same TPLH and TPHL. Okay. Okay, so fan-in considerations. Is it practical to have a large number of fan-in? Okay, so fan-in here refers to the number of inputs. So here we have a fan-in of 4. Okay, for the NAND gate, and basically you can say the propagation delay deteriorates rapidly as a function of fan-in, quadrately in the worst case. So it's not good to have large number of fan-in. Okay, it's better to split into smaller gates. The reason is because if you do like this, and then what is your R equation there? Okay, so your R equation is big. Your C is maybe smaller, but your R equation is equals to RA plus RB plus RC plus RD. Okay, so you have a large resistance. So your TP HL, okay, is high. Okay, especially on discharging. However, your TP LH, okay, when you want to charge it, charging is good. Okay, especially if all is if all is 0, so A B C D all is 0, then we're gonna charge really fast. However, in the case of A B C D all ones, okay, A B C D all ones, then we are going to discharge really slow. Okay, so the idea is okay, so here you can see what is the TPHL, okay, which is quite high. Our equation is high enough, and then you also have the high capacitance, okay, all the capacitance there. Okay, so what is the delay in terms of the fan-in? So if you do a two input NAND, okay, I believe this is a NAND gate. Sorry. Okay, so this is a NAND gate. Okay, so if you have a 2-input NAND, your delay is around 120 picosecond, and then as you increase, for example, if you have a 14 input NAND, and your delay is quite big there. Okay, and it increases quadratically. So gates with spanning greater than 4 should be avoided. And now we go to some of the simple design techniques to achieve good. Remember, our goal is we want a good delay, preferably equal delay, TPHL, TPLH the same. So how do we size the gate to make it the same? So you've seen already, you want to make a 2:1 ratio between the PMOS and NMOS, and you don't want too many inputs fan-in. Okay, so transistor sizing, as long as the fan-out capacitance dominates, otherwise no delay gain, because we reduce the resistance, you also increase the capacitance. So we have to be careful about this. If we increase the size of the transistor, yes, our resistance will go down, but our capacitance will go up as well. Okay, so we have to be careful when we make the transistor too big. This is another method where they go for progressive sizing. Okay, so where your M1 should be made bigger than M2, M3 to Mn. The FET closest to the output is the smallest. Okay, so here you want to make the smallest. Okay, why is this the case? We can do some analysis on it, but I'm not going to go through detail. You can make experiments, and you can see actually that is more efficient to have the transistor closest to the output to be the smallest. And this method can reduce by more than 20% on the delay. This decreasing gains as the energy shrinks. Okay. Transistor ordering is also quite an interesting strategy here to improve the delay, where the critical path, okay, so if you have, for example, here is a 3-input NAND gate, okay, so if you know your critical path, so you want to put your critical path on the transistor closer to the output, okay, so that it can discharge faster. So basically you can discharge, because here discharge already. Okay, here discharge already, so in the end you just discharge only on the top side. Okay, compared to here, Okay, compared to here, you're going to have to discharge the whole thing down. Okay, so delay determined actually by the time to discharge CL only if you put it on the top. Okay, compared to if you put on the bottom, then the delay you have to discharge the whole thing. Okay, so if you know that your critical line is in which pins or of the gate, then you want to put closest to the output. Design technique number 3, logic restructuring. Let's say you need a 10 input NAND. You can break it up and it's more efficient, something like this. Okay, we will look more into detail later on in the logical effort timing optimization chapter later on. Isolating fan in from fan out using the buffer insertion. So you can put you can insert some buffers. Okay, insert some buffers here. Real lesson is that optimizing the delay of a gate in isolation is misguided. So when we try to optimize the size of the gate, we're always going to look at what is it driving. Okay, is it driving a small load? Is it driving a big load? So load here refers to the fan out, right? The fan out of the output. So there's a strategy there. We're going to look more into details later on. How to size the logic gates based on the load that's looking. And finally, I think the last one is reducing the voltage swing. So for if your TPHL is these are high to low, so discharging so discharging through the NMOS, and if it's on velocity saturation. Okay, so here we're looking at the velocity saturation. If you're discharging on the velocity saturation mode, then you can actually reduce your VDD. Okay, you reduce your VDD, you can have a better TPHL. But remember, if you reduce the VDD, you're going to impact your linear mode and saturation mode. So you have to be careful with this. But you can have a linear reduction in delay. Okay, by reducing the VDD, also reduce the power consumption. Requires use of sense amplifier on the receiving end to restore the signal level. Okay, here is the thing that now your output now is not VDD, right? You're going to for discharging, yes, you're going to discharge fast, but when you start to charge it, you're going to charge only up to your V swing, and you will not reach VDD. So you need to bring it back up to VDD at some point. Okay, so I think that's all for this chapter, and the next one will go through the other MOS logic structures.